So yeah, good afternoon everyone. My name is Siva Poornan. I am a doctoral student at the Civil Engineering Department of IIT Madras, and here we are meeting for the fifth week for the course of Matrix Method of Structure Analysis organized by NPTEL. Okay, so we have been discussing on the how we have got started with the main content of how to do a structure analysis using matrix methods. We got started off with analyzing truss elements specifically, right? And then in this session we will be proceeding with that, and then we will be discussing on how to analyze beam elements using similar procedures, right? So in the analysis of trusses, what we saw was first basic, the starting point of matrix method of structure analysis is you first find out the kinematic indeterminacy. You find out what are the degrees of freedom for a given element, and then you construct a stiffness matrix using the methods that we know. Usually we use the force methods to find out. In a truss you can simply find out, so just by finding out, giving unit deformations at each end, and then you can build the stiffness matrix. And then you assemble that stiffness you transform that stiffness matrix, which would be in local coordinate, to a global coordinate, because in a actual truss the truss can be inclined in any direction. Therefore you shift it to, you transform it to a appropriate global coordinate. Once you do this procedure for all the elements, you would be able to assemble them suitably to find out the stiffness matrix for the entire truss structure. So this is what we were discussing last class. So I'd like to take any questions if you have at this point regarding what we had discussed in the last class. Is there any questions on what we had discussed last time? Okay. Okay. Can you reiterate it here? Yeah, sure. Yeah, you can share your screen and you can present the question so that we can discuss on that. It's about the, it's on the beam. Okay, then we'll start discussing on the beams, and then at an appropriate point where you think that it is related to the portion, then you can ask that question. Right? Okay. So no questions on trusses. Okay, fine. Then I just want to point out a few things on trusses before we move on to beams. So first thing is, last class what we had discussed was that so we had said that, let's say P equal to KU. This is what we would be getting in a format. When we do matrix method of section analysis, this is what the usual format that we would be doing, where P is a vector and K is a matrix and U is again a vector. Now we were saying that we would split it into two components. One is a known component and one is an unknown component, right? So this happens because boundary conditions are known at certain points. So U can be split into U known and U unknown. This is what we had discussed last time. So we were asking how to split it if it is not coming consecutively. That also we saw how to do it. Now the question is, sometimes we might not know displacement as well as the forces. Can you think of a case where you would not be knowing a displacement as well as the loading at that node for a truss? Can you think of such a situation? So what you should, yes, what is it? Roller support. If you have a roller support, let's say you have roller support and then you have a truss coming onto that joint, series of truss members meeting at that joint, you know that the displacement at this point, at this direction, you, let's say 1, is going to be 0, right? Because we know rollers can't move vertically to the rolling direction. And about the horizontal direction, right? The horizontal direction, we don't know the displacement, that's right, but we know the force. Yes, if there is an n force coming onto it, we know, let's say there is a P applied onto it, then P is known at that point. So it is similar to that. Degree of freedom is similar to some other degree of freedom that's there here. So for example, if you talk about this node, even in this node we don't know the displacement, but we know the nodal forces that are coming at that end, right? So this degree of freedom is similar to this degree of freedom, is it not? Now the question is, do we know a node where we don't know the force as well as the displacement? Usually, let me think of an example and see, you see whether it makes sense. So let's say you have a truss, okay, and then this point I am not resting on the, or it's resting on a pin itself. That pin is resting not on the rigid ground, not on a rigid ground, but on a soft soil. Okay, let's say it's resting on a soft soil, and you have different portions coming here. Okay, I'm not completing this diagram, but I think there are some trusses are going on here. Okay, now how do you do you know the forces that are coming in the horizontal direction here due to friction or something, or even let's say this roller was not there, this is directly supporting onto the soil, soft soil. Then what happens? We don't know the displacement that is happening in the vertical direction as well as horizontal direction, right? But we don't know the force also. We don't know how much force this is going to offer, how much resistance. This is like a support, right? So vertically we don't know how much support it's going to offer. It's a support reaction. So vertically we don't know the force, we don't know displacement, we don't know the force also, right? P, which is in the direction of delta. Is this right? What is it? It is an actual. Yes, so yes, exactly. So yes, that's a way to solve it. So if we are having such a situation where both of them are unknown, then what we have to do is we have to characterize the soil. We have to find out what is the stiffness offered by this soft soil, and if we know, if we find out doing tests, how can we do? We can just take the soil and then we can. There are standard procedures. I'm just giving a very basic idea of what to do. So you can apply force and then you can see how much is the displacement. That will give a indication of what is the stiffness of the soil, right? So once you know the stiffness of the soil, you can replace it with a spring. So instead of having this whole soil, for modeling, you can say that you have a spring there, which with known stiffness, right? So once this spring is replaced, and then you can say that this spring is on a hard portion of the soil. So now we know this. We have to find out characterize the stiffness of the soil. So now if this is the case, then we can do a structure analysis like an usual thing. At this point, we don't know displacement, but we know the forces that are coming from external. Right? It's just another node like any other nodes here. We know the stiffness and so on, so we can solve this problem. At this point, we know that displacements are going to be zero, right? So at least one thing is known, so we can do that. So that is one thing that I want to point out, that in every case it can be converted to a situation that we either know the displacements at a point or a force at a point. Okay, so once it is done, then we can solve it using the procedure that we have discussed in the earlier session. Okay, that is one thing. Another thing is, let's say that the displacement is not zero. It is a constant amount and it is not zero. Why I'm saying is, what we had said last time is this known displacements are going to be zero, right? This is what we had said last time. But what if they are not zero? They are known but they are not zero. Let's say it's 2 units, like that we say. So how do we solve it then? uh, will it also have a similar, like, will it change the way in which we discussed last time? Will it change anything that we discussed last time? So last time what we had seen was that we can solve only the bottom portion is what we saw. We can eliminate uh, whatever 0 degrees of, if the known is there, then we cut out the first row in the first column and then we can take only k to 2 and we can solve. This is what we had discussed last time. But now that this known displacements are not 0, if it is finite, what should we do? Can we do the same thing? Can we write pt equal to k to 2 into uu? Yes, so there will be an effect of UK also, which has to be considered. So how to consider is just expand that the whole thing and then you will find it out. Okay, so you write it as uh, so this thing, taking off the rows and columns for the known displacements will work only when the displacements are zero. That is what I want to highlight here. So don't take it any time that if it is known, it has to be just those rows and those columns should be taken off. That is not always true. So you get an equation P1 is equal to K11 into 2, which is UK here, plus UU into K12. So you can solve for this actually. So P22 will be, P2 will have a known component. It will have K21 into this known component plus K22 into U2. So I'm sorry. So this is the equation you have to solve first. So you'll have an contribution from K21 as well, which was not there last time. Okay, fine. So these two things I wanted to highlight this time. Mm, okay, I hope this is clear. Behave like what? You are saying it will the displacements will not be known and the forces also will not be known. That case or this one? Yes. Yeah, because even there you don't. But if you consider everything to be a part of a system, you don't need to worry about which is primary, which is secondary, and so on. Like it is anyways as a part of a system, you will know the stiffness of each joint, so you can assemble them, and then it will get incorporated in the stiffness matrix itself. Anyway, here also we are doing that only. We are saying that we will incorporate the effect of soil as a member itself. If only we treat it as a boundary condition, then the problem comes, right? So you're right. So if you have a secondary beam and then you're having a primary beam, then if you treat this secondary beam as support condition for this primary beam, then the problem comes. You don't know what is a support boundary condition, how much displacement is happening in the boundary condition. But treat it as a system itself. Treat it as a whole with the system and consider the boundary somewhere else where it is rigid. If you do that, then there is no problem at all. I hope that is clear. Okay, fine. Then one more thing I wanted to just ask. Uh, let's say you have a complex system, okay, some complex system I'm drawing. Okay, this is like a truss system. You have 2D truss system, and then I am not going to have loads in all the nodes. Okay, there are so many nodes here, but I'm not going to have nodes everywhere. I'm just going to have a member like this, and then apply force only here. Okay, F1. And let's say I'm having another member, and I'm just going to pull this member F2. Okay, now let us say that. Okay, this member might be unstable for horizontal loads. Just say that there are no horizontal loads. Okay, so I'm just going to pull it, I mean there are no vertical loads. Okay, so I'm only having horizontal loads, so therefore that member will stay upright. Now the question is, if I treat this whole system as a spring, okay, where F1, this is also F1, okay, both will be should be same, right? So you have F1 and F1. Can I treat it as a, is it, should it be possible to treat it as a spring? Because for a given load I should be able, there will be a deformation in the system which can be imagined as a spring, which will also have the same deformation for the same given loads, right? That means that I need to build up a system with only 2 degrees of freedom. This is u1, let's say this is u1 and this is u2. So basically I should be able to build a stiffness matrix. This is f2, which is same as minus f1. Okay, you can later on, just for illustration purpose, I'm taking it as f1 and f1, f2. So I should be able to build a 2 by 2 matrix, is it not? Just like a normal truss member, whatever we built a 2 by 2 matrix, right? Similarly, can we build a 2 by 2 matrix here is a question with an U1 and U2. So what are this K thing that we have here? How to find out this matrix? Yes, partition. Okay, so let's say that this is having how many nodes? I don't know. Maybe we can count. Let's say 8 nodes. Okay, some number. Yeah, six. Okay, fine. 1, 2, 3, 4, 5, 6. Then you can treat these also. Right, 8, right? 1, 1, 2, 3, 4, 5, 6, 7, and 8. Okay. These two nodes are important. These two nodes are only the things that we want actually, and other nodes we don't want. Okay, so because we know that there is no going to be no force there, even though the nodes are present, if only the forces are going to come, then we need a 8 by 8 matrix. We'll have 8 forces and 8 displacements. But now we are only 8 into 2 maybe. Okay, so now we are wanting only at certain nodes, right? So then how do we do it? So how do you? We'll have some. We know how to. So we know to build this F6 16 forces, and we will build a 16 by 16 stiffness matrix. This procedure is known to us, right? After this, how to reduce it into 2 by 2 system, or even 4 by 4 system. Let's say forces are allowed to come here. Let's say this member is instead of being straight, let us a triangle or something, so that is not unstable. Okay, okay, something like this maybe. Okay, so then you have 16 thing. You want to reduce the 16 by 16 into 4 by 4. How do we do that? We know we want to retain only F1, F2, F3, F4. Okay, which corresponds to F1, F2, F3, F4, and all other things are intermediate. Okay, so how do we do that then? So we have to do a similar thing like what you said. Let's say this is the needed points. Okay, let me write it as F Roman 1, and F2 is all the interior points. Okay, which we don't want. Yes, and then we have this K, and then you have this same so corresponding displacements, right? U1 and U2, and this whole K can be split into 4 components, right? F1 2. Okay, let me just write 1 2 just for sake of simplicity. Okay, F11 1 2 K21 and K22. Now what do we do after this? Yeah, so we'll have two equations. We have to just solve for them and then substitute. So basically we need to solve for this. Okay, so how do we solve this? Just take the two equations. F1 is equal to K11 U1 plus K22. But one condition we need to impose here. What is known in this whole thing? In this whole matrix that we have written, one thing is known to us. We know that F2 is going to be 0. Is it not? Because we know that there are going to be no forces there. That's the whole reason why we want to split it into only two. We want to condense it. This process is called as condensation. So we want to condense the whole matrix into a simpler matrix because we know some of the degrees of freedom are not going to be used. There are not going to be any forces. So we need not have so many degrees of freedom. We can reduce them. That's what we are doing now. So we are having this equal to 0. So we have this first equation, and K2 1 2 into u2, right? And similar second equation just becomes 0 is equal to k21 u1 plus k22 into u2. So here we can solve for u2, find u2 from here in terms of u1 and substitute it here. So what is why? Because we don't want u2. U2 is an interior thing, right? So we are replacing u2 is equal to minus k22 inverse k21 u1, right? This is what u2 will be if I just replace this, right? So I can substitute it here. I will get f1 is equal to k11 u1 will just stay still plus k12 into u2 is this thing. So I can write the whole thing. Let's say this is just some k dash. Okay, just for simplicity I'm doing this. So I can write it as k dash into u1. So I can take u1 common outside, and the leftover part will be the reduced thing. So I know f1 is equal to some k reduced into u1. So I am now able to write f1 in terms of just u1, where kr is nothing but k11 plus k12 into k dash, where k dash is nothing but minus k22 inverse k21. Okay, so this process of condensing the whole stiffness matrix into a lower degrees of freedom is called as static condensation. Okay, So this is not restricted to just stress analysis. You can do the same procedure for even beams and other things. As we will proceed on and discuss about beams, it will get clear. But the process of why, uh, the way of what we are doing here will remain constant, even for beams and frames and so on. Only the stiffness matrix, how we build the stiffness matrix will be different, but the whole process will itself remain the same. So once you understand trusses thoroughly, you don't need to worry much on the other concepts. Okay, so I hope this procedure is also clear. Okay, then we'll move on to the next concept of how to analyze beams and what is different in that. So how many degrees of freedom does a beam have? 6 degree of freedom. Why? What are the degrees of freedom at each end? So a beam by itself, by definition, yeah, but then definition of a beam in itself is that it does not have actual degrees of freedom. Okay, right definition of beam is like that, but in general we take it as a beam column and then we include actual different. Beam column is nothing but a frame element, right? So we can include, but in general when we say beams, we don't have any actual degrees of freedom. Okay, so it will have only vertical and rotational degrees of freedom. So we'll have 4 degrees of freedom here, and then that means that, so we have seen this concept even in an earlier topic. We say that it will have 4 degrees of freedom, and it thus means that the deformation profile will be a cubic equation, right? So it will take a shape of a cubic curve at max. It cannot take anything more than that, because we have seen why, because the bending moment will vary linearly. Therefore the displacement profile will be cubic, which means that we have 4 unknowns there: ax cube plus bx square plus cx plus d is equal to 0 is what the nature of the is equal to y is what the nature of the profile would be. So a b c d are the 4 unknowns which are represented as degrees of freedom in this concept. Okay, so um, you have four unknowns here. These 4 unknowns will give rise to, these 4 unknowns are the degree displacement degrees of freedom u1 theta 1 and u2 theta 2. So now we know that this 4 things should be related to the corresponding moment and shear forces that are applied at those points using the stiffness matrix. Right? From our previous knowledge, we know that force and displacements are always related linearly. Therefore, we have m1, m2, m3, I mean, um, yes, v1, m1, v2, m2. Okay, correspondingly, v1, m1, v2, and m2. So v2 and m2 should be related to these degrees of freedom using a 4 by 4 stiffness matrix, and so on till theta 2. Okay, now how to find out the stiffness matrix? So we know it will have 16 elements. So how to find out the stiffness matrix? A very formal systematic way of doing it is, last class we didn't do it that way because we wanted to make it very simple. This class, if we have to make it more systematic, then the proper way of doing it is, we say we'll obtain it column wise. Okay, how do we obtain each column? Is that we'll say that we'll have only 1 degree of, basically for this you need to understand how matrices are multiplied. So if you have a matrix under column multiplication, okay, let's just take 4 elements. Okay, so let's say 1 2 3 4, and here you have 5 and 6. This actually means that you are having 1 and 3, the column, multiplied by the first one 5, plus 2 and 4, the second column, multiplied by the second element 6. This is what it means actually. That is what will be the actual column that you are going to get on the left hand side. Okay, so if you have an unknown, this is one way of seeing matrix multiplication. If you are able to visualize it this way, then you can understand why, even in the last session we had discussed that if we interchange these two things, then we should change the columns. 1 3 should go here, 2 4 should come here, because basically they have to multiply correspondingly. Okay, that's what. And even here why I'm saying is, if you're able to visualize it that way, then you know that this first column is going to get multiplied to u1. So if we want this first, what is it? Can you please repeat it? this plus sign. Yeah, it should be right. Basically, see, we want what will be the result of this matrix and into vector multiplication. This is 2 by 2 and this is 2 by 1, right? Yes. Yes. No, how do you add vectors? Let's say you have 1, 5 and 2, 8. If you want to add vectors, how do you add? What is the result of these two things? Yes. Yes, right. So it's still a vector, right? So these vectors will correspond to two different equations only. These two numbers still. Adding corresponding elements of a vector would not, in, it would not it would not, okay, it would not do anything to the equation. It will just correspond to the same equation. Okay, so basically the result of 2 by 2 and 2 by 1 is still a 2 by 1. That 2 by 1 can be imagined to be a linear combination of the columns in the matrix. Okay, these two columns are there, right? A linear combination of them. 1, 3 is multiplied by some number, 2, 4 is multiplied by some other number, and a linear combination of them is what will be the resultant vector. This is one way of seeing matrix vector multiplication. There are different ways in which you can visualize, we can understand it. This is one of the ways, okay? And if you understand it this way, whatever we are going to discuss now will become simpler. So, why I'm saying this is basically if you want to obtain one of the columns, then what you have to do is that you have to make this number as 1 and this number as 0. Once you do that, and all other for if there are more columns, corresponding numbers everything should be made 0, so that only this number will become this number, whatever you have here, right? That's what exactly we are going to do. We are going to take this column, take it as 1 here and make 0 everywhere else, and then we do a structure analysis, force method of structure analysis, or whatever we have studied from previous classes, and then we find out what is this corresponding unknown forces. That will be the column, first column. Similarly, you find out all other columns and you fill the whole matrix. Okay, then how do we do this? U1 is equal to 1 and everything else is 0, right? What does it mean? If you have a beam and if u1 has to be 1 and theta has to be 0, then what it means is that it will have a unit displacement here and rotation will be 0 here, right? So the rotation will be 0 here, so it will have, maybe I can choose a different color. So it, yes, yes, exactly, guided roller is what. So you will have 0 displacement here and then 0 rotation here, but unit displacement, and then you will have this. So this is like a fixed support. Now, whatever is the forces generated at each point, we have to find out V1, M2, V2, M2, right? What it means is that what is the shear force at this point? V1. Shear force means the applied force, right? At that point. And M1 is a rotation or the fixed moment. You will have a guided roller support to make this happen. What will be the fixed end moment that is being produced there? M1. And similarly, you have shear force and moment being produced here, right? M2 and V2. So we find out we calculate these forces. So what is the easy way to find out these problems? Maybe we can do a complex structure analysis and then we can find out this. So yeah, slope deflections you can do multiple things, but what is the easiest? You can actually do it by a very determinate process if you use symmetry and if you're very good at imagining things, right? And you can develop that. It's not very difficult. So what I'm trying to say is that, let's say what we have drawn earlier is that you have a beam and then you imagine it's a guided roller. So we said that this is the deflected portion. Okay, now can you see there is a symmetry about the center? A kind of symmetry, because this portion deformation wise it looks very same to this portion as well. Not displacement wise. Displacement is an absolute thing. A deformation is a relative thing. So basically I'm saying that if I take this portion and then somehow rotate it and flip it, can I merge it with this portion? It seems so, because the rotation is 0 at this end and the rotation is also 0 at this end. And then if you can see that this is just like a deflection of a cantilever, there is also deflection of a cantilever, right? This portion. So basically, if you understand that, then basically you can solve this problem. You know that you take this half portion, this is L by 2 portion, right? So I take this half of this or the other half, whichever you like. Okay, both are going to be same. So I'm going to apply a what force? Let's say some P force. Hmm? What is the deflection? Deflection produced should be, we know that this whole deflection should be 1, right? Then because of symmetry, we know that this deflection should be half. Both the cantilevers should deflect by the same amount, right? Because of symmetry. So we know that deflection is half. That means that we know what is the deflection due to P, right? In a cantilever, what is the deflection due to P? Yes. So these formulas, if you are knowing, then you can use this method. PL cube by 3I is equal to half. So you find out what P is. And here L is not L, okay? L should be L by 2. Yes. So let's just denote it as L dash, okay? So just substitute L equal to L by 2 and then find out what P is. You can do this calculation, okay? I'm skipping it. Once you do that P, that P is going to be the same P that you're going to apply here, because if you think about this, okay, if you have to produce a P here, this will be P and this will be P here and this will be P here, right? So this P is what we called as V1 or something like that, right? So this P is going to be V1 and this P is going to be V2. Okay, that is the same P that we are going to calculate from this equation. So once you find out that, you will find that that is the V1 and V2 are known immediately. This V1 is known, V2 is known. Okay. M, if you want to find out M, it is also simple. P into L dash will give you M. That's it. Okay. So L dash will be L by 2. So if you have this, you will find out to be 12, what is it? 12 EI by L cube. Yes, right? So if you multiply it by L by 2, what happens? Why L by 2? Because this is L by 2, right? So if you multiply by 6 EI by L square, right? And that comes to be M2. And that will be same as M1 here for this cantilever. So you can, in that way you can find out, and signs you can find out by just imagining what sign it will, whether it will be anti-clockwise or clockwise. Anti-clockwise means positive and clockwise you take it as negative. So depends on sign that you adopt. Need not be the same that what I am saying, but you be consistent on what you use. So this way you can easily solve this problem. So this is for the first column of the stiffness matrix. What about the second column? Second column means that you have to keep theta 1 as 1 and everything else as 0. The deflected shape would be something like this. You have only unit rotation and 0 rotation and 0 displacement at all ends except this portion where it has unit rotation. This thing we have already partly seen. It is similar to a propped cantilever, right? A propped cantilever with a moment, we know what is a moment to apply so that you have unit rotation. We have already discussed about this concept. So we have M is equal to 4I into theta, right? So we know that here theta is going to be 1. So I'll just replace this at 1. So you find out what is the moment that you need to apply for this unit rotation, right? And half of that moment will be produced at the fixed end. That also we have seen. So you can know M1 and M2. You can also find out the shear forces just from equilibrium, right? So these two moments actually will be, I think I'm drawing M2 in the other direction. It should be clockwise, right? Anti-clockwise, I mean, right? So you have M1 and M2 are in the same direction. So if this is going to be 4EI by L and this is going to be 2EI by L, which we know it's to be half of what we applied, then the total moment in the structure is going to be 6EI by L, right? And 6EI by L should be compensated by the shear forces. So this is total is anti-clockwise, so we need to produce a clockwise moment through shear force, right? This is also anti-clockwise, this is also anti-clockwise, total is 6EI by L. That 6EI by L will be compensated by 6EI by L square. L square here and 6EI by L square here. So when we multiply both of, when we take couple due to these forces, it will be into L. So it will be 6CI by L, right? So that is how you easily solve these problems instead of using very complicated. Not complicated. It might be easy if you practice, but then this will be very intuitive. Okay, fine. Okay, so similarly you can solve for K3 and K4, which I mean the third column or the fourth column, which I will not discuss because the procedure is very similar. K3 will be the third column will again have a similar deformation as the first one, and fourth one will have a deformation very similar to the second one. Just in the second, in the other side, that's the only difference. But the deformation profile is going to be same. So the way in which you find out the unknown forces, support forces will be same. Maybe just negative signs will differ here and there. Okay, so you can do those things. So that's how you build the whole stiffness matrix for a beam element. So now we know how to relate the n forces v1 m1 v2 m2 through known stiffness matrix through theta 1 um, u1 theta 1, right? So u1 theta 1 u2 okay. So once this procedure is there, then we know how to assemble we know how to um, if we do the same procedure for all the beam elements that are present at a joint, then we can assemble them appropriately to build the whole beam matrix for a whole stiffness matrix for a entire structure consisting of many beam elements. So you could have a problem where you have something like this, right? So you have something like this, then you know that there are two beam elements. In both the beam elements, you have to first assemble the stiffness matrix. You have to find the stiffness matrix, the 4 by 4 stiffness matrix, and then you have to assemble them such that the degrees of freedom at this points are getting added. The stiffness at the degree of freedom points are getting added, right? And this is a similar procedure to what we had seen for trusses. So I think we don't need to get into too much of detail of how we assemble it, right? So you just need to have a 4 by 4 stiffness matrix for one thing and 4 by 4 for the second thing, which will overlap with this thing, because totally you have only 1 2 3 4 5 6, so totally there will be only 6 degrees of freedom. This 4 is what we have built from here, and this 4 will be for the second thing similar to this. Then at this point it will just get added, right? So you will have 1 2 3 4 5 6 degrees of freedom. Similarly the other side, right? Okay, so once this is known, then you can relate the moments, the shear forces and the n moments and the n forces to the displacements or rotations at the nodal points in the global axis, right? So you'll have a 6 by 4 force vector, 6 by 1 force vector, which can be related to a 6 by 1 displacement vector through a 6 by 6 total global stiffness matrix. Okay. So once you know these, you can solve for we can use a similar procedure. Whichever displacements are known and are equal to be 0, you can take the rows and columns, corresponding rows and columns off, and then you can only use the reduced stiffness matrix to solve for the unknown displacements through the known forces at those degrees of freedom. Fine. This part of the process is same as what we had discussed for the truss case. So I'm not discussing that in detail, unless you have any particular questions on that. Right? So before we move on to further topic, I just want to ask if you have any question. You said you have some questions on.
Yeah, I have a question. Actually, it's not kind of question. That's only.
Okay.
But I think it's a controller in the circuit.
Okay. Okay.
And the support unit.
Sure. Yeah, I think you would be able to present even without me closing it, right? Yeah, yeah, I can see your screen. Yes, yes. Okay, can you please show the question first so that I mean the figure. Okay. Yeah. Okay. Okay. No, you don't need to show the entire thing of what you have done because this recorded lecture will be available to public. So I don't want you to discuss a solution here. You can just ask a question. What is your problem what you face in solving the? Okay. 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 Okay, I'll raise this issue to the NPTEL and the concerned authorities and see what it is. Anyway, as of now, what you think is the would be the answer that they expect. You can put it and then see what happens.